So, but 5 minutes is about how long it should be, right?
Yeah.
Or less. Okay.
That is correct. In between 3 to 5.
Okay, and should I be looking anywhere in particular, like out of the audience or at the camera or
To
anything?
the camera.
Okay. And just whenever I'm ready?
Whenever you're ready. We've got lots of time.
Yep. Alright. So hi, I'm Thomas Crowell, and my research is regarding efficiency of the k-means algorithm and trying to get effective speedups in the algorithm by using data structures and parallelism. So the k-means algorithm is a popular clustering algorithm based on essentially taking k center points and looking for the closest points in distance to those center points, and then iterating and taking the means of all the points in that group until we converge and into some set clusters. K-means is a popular algorithm mostly because it's simple, but we'd like to make it fast because it's not particularly fast right now. So some previous work that's been done with this is trying a variation called the mini-batch k-means algorithm, which is we take a sample of our total point set and we run k-means on that, and that's been shown to essentially give us a good enough approximation in a much faster time. Another improvement that's been made is using a KD tree type data structure for k-means, where we want to split our point set into cells where each cell will become smaller and smaller until it's just an individual point, and it can be essentially stored as a tree where parents and children of the tree are more closely related in distance to each other. So that's another way. And one more way that the k-means algorithm has been improved previously is through parallelism. So we can hand each individual data point to a processor, which can more quickly find the distance between those points and all the centers than doing it sequentially and individually. So the approach that I am taking in my research is to take this KD structure and try to implement it in a parallel fashion. So the main challenge in this is that when we use this KD data structure, KD tree data structure, we lose the inherent parallelism that we have with sequential KDs. So it becomes more challenging to distribute all the points to all the processors. So instead we get individual subtrees of this KD tree and work with those. But another problem with that is that they're not necessarily balanced. So we may have processor drift where we need all the processors to finish before we can move forward, but some of them may have more work to do than others. So we can try and average out a workload by giving many trees, and on average it will be quicker. And one more challenge with this is also that I'm looking to do it on GPUs, which is very restrained with memory limits. So we can't store a whole tree with each individual processor. So, and data transfer is very expensive. So we store our whole tree in the global memory of the GPU and then hand individual processors the subtrees when they're needed. So that's my work. Thank you.
What do you think?
It was okay.
You want to do it again?
Do you know how long I was?
You were...
I feel like I must have gone a little long, probably.
No.
Okay.
The only thing is when you're doing your talk, you look at the board a lot,
Mhm.
so you're talking to the board.
I see. Yeah.
And I'm wondering If you have diagrams 1, 2, and 3, can you refer to
Yeah.
numbers instead of having to go and show everybody? That way your voice is totally to the camera.
Yeah. Okay.
So again, we have lots of time, so whenever you're ready, if you want to take a break, walk around.
Yeah. Yeah. I'm just gonna go grab a quick drink of water. I think that's all right.
Yep.
Hi, I'm Thomas Crowell, and my research is regarding efficiency of the k-means algorithm and how we can get speedups using more efficient data structures and parallelism. So the k-means algorithm is a popular clustering algorithm which groups points around k clusters based on their distances from those clusters. So essentially we take all the closest points to that center and look for the closest in that, and then iterate on those and continue to take the averages until we get some set clusters. The k-means algorithm is popular, very popular. Sorry, I'm going to start over.
That's okay. We can even start at the beginning.
Yep. So hi, I'm Thomas Crowell, and my research is regarding the efficiency of the k-means algorithm and getting speedups using efficient data structures and parallelism. So the k-means algorithm is a popular clustering algorithm where we want to group data points around k center points based on their distances from those points, where we iterate and take means to eventually converge on some set clusters. K-means algorithm is a very popular algorithm, mostly due to its simplicity, but it's not particularly fast, so that's where we'd like to improve. So there's been a lot of previous research done to try and improve the k-means algorithm, and one such way is using mini-batch k-means. So the mini-batch k-means algorithm is where we take a sample of our total data set, and we work with that sample to get a good enough approximation of our final cluster centers, and that's been proven to be much quicker than standard k-means and usually good enough for the purposes that we want it for. Another approach is to use a KD data structure, where we essentially want to divide our entire data set into cells where we divide the cells into smaller and smaller groups of points until eventually there's only one point in each cell, such as in figure 3 up on the board. And we can model this as a tree data structure, sort of shown in figure 2, which allows us where the parent-child relationship in the tree also has a relationship that the points are potentially closer to each other than points somewhere else in the tree. So One last way that the k-means algorithm has also been improved is using parallelism. So we can take individual points and hand them to a bunch of processors and let them find the distance between those points and all the various cluster centers, which is much quicker than doing it all sequentially on the individual points. So my approach is to use this KD data structure for k-means along with parallelism. So the challenges inherent with that are that that the KD tree version is not well suited for parallelism. So if we were to just hand each individual point in the tree to a processor, we would essentially just be doing a parallel version and not getting the speed up of using a KD tree. So instead we handed subtrees and let each processor work on the subtrees or a group of points. And so another challenge when we do that is that each subtree may not have the same amount of work in it. So, and that's a problem because if we need to wait for each processor to finish before we can move on. So we adjust for this by handing each processor mini trees and hope that in the end the workload will average out to about the same workload across all processors. And another problem with using the KD tree and parallelism approach is that the GPU, we would look to use parallelism on a GPU, and the GPU does not have a large amount of memory necessarily, so we can't fit our whole tree on each processor. So, and also data transfer is very expensive from a CPU to a GPU. So we first take the tree into global memory of the GPU and only hand out subtrees to processors when necessary. So we limit the data transfer and get the best speed up possible. Thank you.
That was really good. How do you feel?
Pretty good.
Okay. That was about 4 minutes.
Okay.
It's good.
I think I'm probably pretty happy with that.
Okay.
If that's
I thought it
okay.
was good. I'm going to need you to email me your title of either your topic or your research topic.
Okay.
I'm going to put down like, the student's name and the research area of interest or the
Okay.
research topic on the website.
Yeah, okay, I can do that.
Thank you, Thomas.
So not necessarily a thesis title, I guess.
No,
I don't really have one yet.
no, your research area.
Yep, okay.